Hi, everyone. If you don't learn anything from my talk, I want you to learn this one neat trick. This is it. After this, you're free to leave. You don't need to watch the rest of the talk. On your Mac, go to Preferences, Keyboard, Text, and then you can enter in all of these shortcuts. So what this does for me is it translates face. When I type face into that, it turns into that, or hearts, or whatever. Here's a short little video. So if I type in there, and I do face, so that's how I do that so efficiently. All right, that's it, the end of my talk. Thank you very much. Thank you for having me. So my name is Aaron Patterson. I have come from the United States to bring you freedom. America, yeah. My name is Tender Love on the internet. I work for a company called Red Hat. I am on the Manage IQ team, and what we do is we write software that manages clouds. So if you have a cloud, we can manage it. So if you need to do that, please let me know. I want to say thank you to all of you. Thank you to the organizers. Thank you so much for having me. Please, another round of applause for the organizers and the sponsors. If it weren't for them, I couldn't be here. This is the farthest away from home I have been ever, I think. This is my first time in Africa, and somebody asked me, so what do you think, what did you expect to see in Africa when you arrived here? And so I'm going to let you know. So you know what I expected to see. I expected a lot more of these. I did not see any of them. I also expected, I expected Lion King all the time. Nothing. I also expected to hear this song at the airport all the time. I didn't hear that at all. Then I looked up, so I was doing some research, and I looked up a list of South African English regionalisms on Wikipedia so that I could try to relate to everybody here. I don't know if you can tell from my accent, but I'm from the United States. So. When I was a kid, so I'm going to try out some of these phrases. When I was a kid, I used many stiffy discs, apparently. I don't know if I'm using these right at all. I hope this will be a Lecker presentation. Anyway, so came down here, brought my phone, and I wanted to buy a SIM card for it, but my phone was locked. So I went to buy a SIM card, my phone was locked, and they were like, yeah, your phone's locked, you can't get a SIM card. And I was like, what? I paid like $1 million for this phone, it's supposed to be unlocked. So I called them up, and I called up my provider, and they said, yeah, we'll unlock it for you, it's fine. We're gonna email you, and we're gonna send you the unlock code for it. And I got the email last night, and I want to share it with you. So this is the email. I'm going to show you the unlock code here. This is not a joke. I can't make this up. This is literally what showed up in my email. Anyway, so my phone's unlocked now. So this talk is the joy of programming. Joy of programming, and I'm warning you, I want to give you a warning, this is not a soft talk, this is a technical talk. So it might be called Joy of Programming, but this is absolutely a technical talk. I'm sorry, I know it's 9:40 in the morning, but we're going to do tech stuff. I don't care. Just going to do tech stuff. I'm not going to talk about how to find yourself. I don't know how to do that. I have not found myself. I'm still lost. And this, I have to say, this Joy of Programming talk, it is fun for me, not for you. Besides, you probably don't want me to tell you about the joy of anything, because all I do is think about weird stuff all the time, like my freaking cats. Like, why'd I name it that? That's one of my cats. Her name's Choo Choo. She's a girl, so she's wearing a dress. And this is Gorbachev. And then also, I just do weird stuff all the time. Like, this is holiday photos, my wife and I. That's what we did. Our holiday photos. Yes, I paid money for these. So, I want to talk about Rails 5 in action. Room. I love when they use the titles in action or like all these really fast, flashy words, because I don't think that way at all. I showed you. I think about cats and holiday photos. Anyway, so I'm going to talk about three things. I want to talk about bugs. I want to talk about tests. And I'm going to talk about performance. So I guess this is really Rails 5. I'm not really, we're going to be scratching the subject of that. That's like, I don't know, not the main thing about this. This is just, I guess that's tangential to my talk. But the first thing I want to talk about is something I'm really excited about. This is a testing idea. I have a testing idea, and I want to share it with all of you. And I don't know why I'm so excited about this, but I am, because it's just a testing idea. So, okay. I shouldn't build this up too much, I'm sorry. If file A, line B is modified, what test do I run? I always wonder this because we have our tests at work take like 30 minutes to run. And I'm sitting there like, we're trying to upgrade to Rails 4 and I'm refactoring some stuff to like get it to upgrade, and I'm looking at it and I'm like, what test should I run? I have no idea, and I don't want to sit here for 30 minutes running all of them. And I get embarrassed when I send a pull request and the CI fails. So I'd really like to know. So this is the question I want to answer, and we can do this. We can absolutely do this. If you want to do this, go to this page here, and I'll post these slides later so you can grab this link. You can do what I said, but you need to get this patch. I posted a patch here, and if you apply that to Ruby, you can do this. And then there's this mini test extension that I wrote, and you don't need to read the code. Just grab this code from my slides. This is the start of this thing that I said that I want. And basically what it does is just grabs the coverage information before the test runs, then grabs the coverage information after, and then you'll see at the bottom there's a function that says like calculate the difference. You'll notice how that is not implemented. That is what needs to be implemented. So what I would really love is if we had something that was like git diff pipe, what test do I need to run? So apparently this is called regression test selection, something like that, apparently. So if someone can build this, please do it. Please. I really want this. I just don't have time to do it. I have time to run 30-minute tests, but I don't have time to write this program. So please, someone write this. All right. I'm going to talk about memory leaks. This is a really fun bug that we had in Rails. And they're not really memory leaks as much as object leaks. So basically the difference between a memory leak and an object leak is if you have a memory leak is like you allocated some memory and it's never going to get freed, whereas an object leak is like you have too many objects being created and they're not being released for some reason. They're not getting garbage collected for some reason, which typically means you probably have a reference to all those objects somewhere, right? Now, we had this bug. It's bug number 776 in GitHub, which by that number, this is on the Rails tracker, you might imagine how long this bug has been around. And in fact, this bug was around before we had Rails on GitHub. This was around when we had Lighthouse. And what the bug was is if someone does code like this, you open a transaction and you just create a bunch of records in there, this just does it infinitely, you'll get a memory leak, and your memory usage will look like this. This is not an actual chart. This is what the chart may have looked like if you had graphed it. So the question is, why did this leak? And if you take a look at the code, this is what the code looks like. This is not actual code. This is a creative interpretation of the code. Essentially what would happen is you'd call the transaction method, and every record that got created inside that transaction block will get added to an array. And The reason that we added that to an array is because if there was any sort of exception inside of the transaction, we needed to roll back everything that happened inside of the transaction. So essentially, the internals of that transaction method would look like this. Again, not actual code. There are probably some bugs in my creative reinterpretation here. But basically what would happen is if there was an exception, we would catch the error, and then we would roll back any changes that had happened to those records. So for example, when you create a record, we'd get the primary key back, and we would set the ID on the active record object. And obviously, if you had to roll back the transaction, you just set that back to nil. And this is what the actual usage would look like. This is actual code. So if you looked at the record inside your transaction, you'd see, okay, well, the ID is 10, that makes sense, but something happened, so we're gonna go back outside. We still have a reference to that object, and we need the ID to be nil again, because it didn't actually get saved in the database, okay? This is actual code. I love that rescue statement. That's, you're not the boss of me. I'm gonna rescue you, I don't care. Anyway, all right. So the reason this leaked is because we had this transaction object, and this transaction object was pointing at all of these record objects. As soon as you created one, it would point at it. And we had a root. The root was pointing at the transaction, so all of those records were connected down to a root, and we would just keep allocating memory over and over, and it would grow infinitely. So if you created an infinite number of objects inside a transaction block, you'd have an infinite amount of memory used. So how do we fix this? The idea to fix this back in the day when this was filed was to use a weak ref. And what would happen then is we would have weak references here indicated by those dotted lines. Essentially what would happen is if nobody was holding any references to those records would get garbage collected. So, you know, maybe only those two records there were, somebody was holding references to those two records, so only those two records stuck around. What that means is that we would only roll back live objects. So any objects that were actually live, we would roll back the data on those. Now, unfortunately, back then, weak references did not work on all Rubies. It just didn't work. In fact, I don't think it worked at all on MRI. Just not at all. So we didn't do that, and the bug just sat there. It sat there for about, I don't know, 4 years or so. And finally, I came up with a solution and made a student implement it. We've been working with, so the Rails team has been working with a bunch of university students. Every year for the past, I guess, 3 years or so, we've been working with university students from around the world for about a quarter, or one of their quarters at the university. So essentially, we find problems that we don't want to do. And give them to the students. Anyway, so the solution to this problem was we take this. So this is what our tree, our object graph would look like. And what we decided to do is just flip those arrows around such that they pointed back at the transaction, right? That way, if you're holding references to those two records are now roots. And the rest of those would get garbage collected. But what this meant was that we had to add a little bit of complexity to some of our methods. So here's an example of the ID method. What it would have to do is say, and again, this is not actual code, although I didn't put it at the bottom there. We would have to say like, hey, am I inside of a transaction? If I'm inside of a transaction and it's been rolled back, I should return nil. Otherwise, I'll just return whatever was sent, what I'm sent to. So that was, our code got a little bit more complex. All of the attributes that we needed to roll back, like this one, the created on dates, the updated dates, those ones, we had to sync up with the transaction. So we're lazily rolling those methods back. So anyway, fast forward to recently, we had another, like one of the engineers on the Rails team decided, well, you know, now we've got weak references and they work across all Ruby implementations, and this code is somewhat complex. We had to add a little bit of complexity to the system. Let's switch it back. We'll switch it to weak references and simplify the code. So I am deathly afraid of weak references. At first I thought this fear was unfounded. Like, I just thought something was wrong with me. But what I'm going to do is I'm going to tell you, I'm going to articulate exactly why I'm afraid of these things and why we're actually not going to be using them. So what the idea was is we would say, all right, when we create a record inside of this transaction block, rather than adding the record to this array of things, we're going to add a weak reference, and that weak reference is going to wrap up the actual object. So that's those few lines at the top. And what that means is we can get rid of this implementation. This implementation can go away. So basically what we do down here is if there's an exception, we check if the weak ref is alive. If it's alive, we roll back the object. It means we don't have to have this implementation. It can just go back to this, right? So much easier implementation of the ID method. So now the problem is these arrows stay alive. So a weak reference is still an object. The thing that a weak reference points to will get deallocated, but the weak reference itself won't be deallocated because we have to ask it whether or not its reference is still alive. So if we're creating an infinite number of records, we're going to create an infinite number of weak refs. So my question was, are weak references free? And the answer is no. They are not free. They cost about 40 bytes each. Now the interesting thing about this is that the size of the weak ref is actually less than the size of the active record object. So if we as we're creating these weak references, we'll still get a leak. It's just that this leak will be much slower than if we were adding active record objects to this array. So my problem with this is that a slow leak is still a leak. Now, the other thing that really, really bothered me about this is we essentially have random code execution in here now. And what I mean by this is if we look at this loop here, we're saying, hey, weak ref, are you alive? If you're alive, we're going to roll you back, right? But the problem is that objects can be collected at any time. So if we look at this, we wonder, when is that going to be collected? When is alive going to return true? And we really can't predict that. We don't know. It's random. So the other side of this is that means that when we roll back these objects, so we have this giant list of objects that we need to roll back, we're iterating through all of them. We're looking at them, we're saying, hey, are you alive? We don't know how much that's going to cost. So let's say we allocated 1 million records and no garbage collection happened. It's going to cost a lot more to roll back all those objects than if garbage collection had happened. And we don't know whether or not that's going to happen. We don't know if garbage collection is going to happen at all. This is especially a problem for people who tune their garbage collectors such that they don't run as frequently. So we have random performance, ON performance with a random little thing inside here. And I thought to myself, you know, imagine the bug reports. Imagine the bug reports that are going to come in. So this is my most favorite way that a bug report starts out is sometimes. I get this look on my face. I'm like, sometimes. Sometimes it's slow. Sometimes sometimes this code is called. These are things I never ever want to see in my issue tracker. So I thought to myself, you know, should I use? You might be saying, should I use weak references? And I'm going to say to you, I don't know. Possibly. I don't think they're particularly good for this. I don't think they're good for this particular issue. But the point that I wanted to make about this is that, you know, even though that code was simplified, even though these weak references simplified our implementation, this simple code may not be so simple, right? We simplified that code, but it actually has very complex side effects that we need to know about. And I'm afraid that sometimes we spend too much time chasing this simplicity dragon. We're like, we need to make the code as simple as possible, make it as simple as possible without thinking about the side effects of that. So, all right, I'm done with weak references. Scare me. I want to talk about integration tests now. How many people write integration tests? A few? All right, yes. I love integration tests, but I don't write them. Okay, I do write them, but not so much. So let's look at a controller test. This is a controller test. You don't need to read it so closely. Now back to an integration test. Now controller test, integration test, controller test, integration test. They look almost exactly the same, So I thought to myself, like, why do we write controller tests? Why do I bother with controller tests when I have integration tests that do almost exactly the same thing? And then I figured out, like, the reason I write more controller tests than I write integration tests is because integration tests are slow. This is the only reason I was writing controller tests, just because the integration tests are too slow. And then I thought to myself, well, you know, if the tests are slow, is the website slow? And I don't think that's true. I don't think that, I mean, the website is fast enough to serve up pages to all of our clients. If the website is fast enough to serve up pages to our clients, why are our tests so freaking slow? Like, it doesn't make sense to me. Something does not add up. It just doesn't make sense to me. So for Rails 5, I want to have fast tests. And I want to delete functional tests, but not actually delete functional tests. I mean, delete our functional test framework. So essentially, functional tests would still exist. It's just that we would translate them to integration tests, and you would not know that. So I was wondering to myself, why are these tests so slow? Why are they so slow? It just bothers me. And I have to give credit to Eileen Codes here for she's written most of the benchmarks that I'm going to show in these slides. So I'm like, okay, well, how slow are they? If you're going to say they're slow, we need to figure out how slow they are. And the way that I do this is I use a tool called benchmark IPS, and this benchmarks the number of iterations per second that a particular piece of code can run. This is what our benchmark looked like. And essentially what it's doing is comparing those two tests I showed you earlier, the integration test versus the controller test. And down here at the bottom, we have this method called compare, which actually just produces a comparison of the two. It says, like, this one is slower than this one by so much. So we ran this benchmark, and this is what the results look like. And you'll see down here, that's the comparison. So integration tests are about 2.47 times slower than controller tests, which is really freaking slow. So I thought, okay, what is so slow? We know that one is slower than the other, but what part about that one is so slow? Let's try and figure that out. The tool I use for that is a tool called StackProf, and what this does is this is a sampling profiler that will run against your Ruby code. It'll take samples of the stack and show you where your time is being spent. So this is the code I used for this, and I said, okay, I'm going to do, at the top here, we ran one request through. This is basically just a warm-up, make sure that we've got any caches heated up that we need to, and then we did a CPU profiling test against this. And that CPU profiling test was dumped to a file called stackprof.out. Okay, so I want to talk a little bit now about CPU time versus wall time. You can run StackProf in CPU time or wall time. There's two different modes you can put it in. And what that is the CPU profiler will tell you about time spent on the CPU. So this doesn't take into account system calls like sleep, for example. Sleep is slow, but it doesn't use up your CPU, so it's not going to get reported in a CPU time profile. Whereas it would show up in a wall clock profile. So I ran this to look at the controller bottleneck. I wanted to know what was bottlenecking controllers first, just to get an idea of the stack there. And I viewed the stack. Now, out of the stack came this. These were the top five offenders. That number one there is mini-test runnable on signal. So 53% of my time was spent in mini-test runnable on signal, and I was like, wow, that's amazing. 50% of my time is spent in mini-test? Well, if I speed up mini-test, if I delete this method, then our code should get 50% faster. So I'm like, okay, well, mini-test is slow, so I took a look at the method. It does a bunch of stuff. What this method does is it sets some traps. So when you're running your Rails tests, what this does is you can hit Control-T, and you'll see test output. So this is capturing that signal. And I was like, all right, well, you know what? Let's just delete it. I don't need that now. We'll delete it and see if our code gets any faster. So I do this, just deleted the whole thing. And then I ran the profiler again, and this is the profile output, which was really amazing. I cut that one off the top, and I was like, this is sweet. My code is 50% faster. So I've reduced it by 50%. I was really, really excited. This is my face. It was really exciting. So I was like, all right. So, it's 50% faster. Let's actually just run this with the time command. And I did that. I said, okay, let's time it. This is the first one. The first one took about 12 seconds. And then I timed it after my speed improvements. And after my speed improvements, it took 12 seconds. What the F? Why is this? Why did this happen? So I knew that this process was CPU bound, because if I looked at the machine while I'm running this test, you can see it's using 100% CPU the entire time, right? So if you're using CPU 100% of the time, if you're pegging out the CPU, then your wall profile should be similar to your CPU profiles. They should be very similar if you're CPU bound. So this is what it looked like with the CPU bound. Oh, do I have slides about? Yes. So this is what it looked like when I did CPU stacks. And the next one, which I've completely mislabeled at the top, that's actually wall speed. And you'll see that those two stacks are completely different. So CPU time, we have on signal at the top. Wall time, we have per thread registry instance at the top. They look completely different. So I couldn't believe this. The times, I thought I had improved my code by 50%. I was extremely disappointed. So I went and spoke with Aman Gupta, who wrote the profiler, and I was like, hey, something seems weird about your tool. It showed me that if I deleted this method, my code would get 50% faster, and it did nothing. And I showed him all the stuff, and he's like, yeah, that is weird. And I was like, thanks. It's not what I wanted to hear. So then I talked to Koichi Sasada, who's the VM implementer, and I was like, hey, Koichi, I ran into this issue. I'm trying to speed up this code. Aman says that the profiles look weird, but that he's actually getting the data from Ruby itself, so I should talk to you. So I was talking to him, and I walked him through the entire problem, showed him these stacks, showed him the two different outputs, and Koichi says, yeah, that is weird. And I was like, come on. So it turns out that it is a bug, and we don't know where, but it's only when you use the trap call, the trap method, and it's only on OS X. Only. So if you run this same profile on Linux, both the CPU and the wall profiles look like this one. It doesn't look like this at all. This is only on OS X. So unfortunately, even profilers have bugs. All right, so I modified that code and I didn't speed it up at all. So let's do something useful. All right, do something useful. Let's actually profile integration test. Now that we know that the CPU time, we know that we're bottlenecked on CPU, and we know that the CPU time profiler is broken, so let's just use the wall clock time. So if we profile integration tests using the wall clock profiler, we'll see at the top there that the number one method, the number one offender is module delegate, and apparently calling delegate is slow. So there's this method in Rails called delegate. If you call that, it's super slow. So this is the patch I applied. Basically, I re-implemented those delegate methods just in Ruby. I rewrote them. Then I checked my progress because before I checked the progress, and I made no progress. So let's see what happens. We started out at 2.4 times slower. With that one patch, when I compared against controller tests, now we're down to 1.45 times slower. So we actually did improve the code here. We did 2.4 times down to 1.4 times, and we can verify again here. If we run against time, we'll see before the change it was 26 seconds, and then after the change it took about 16 seconds. So again, even profilers have bugs. Always measure and verify your results, okay? So I want to talk about something else now, memory savings. The next thing I want to do And again, I'm going to make when I say I'm going to do this, what I really mean is I'm going to make a student do this. I don't have time for this. Make a student do it. I want to do some copy on write improvements to Rails. I'm going to talk about this a little bit. So, I don't know how long I've been on the Rails core team, a while, and I always thought that Rails worked the way that I'm going to describe to you, but it never did. So, I'm going to talk about Rails template compilation, and it turns out Rails template compilation is lazy. So all template compilation in Rails is lazy, and what that means is when a request comes in, what we do is we get a lock, and we say, hey, is that template compiled? The template that we need to render, is it compiled? If it is compiled, then we just return it and unlock. We're done. If it isn't compiled, then we compile it, save it off into memory, and then return it and unlock, and we're done. Now the problem is that this save part here actually writes to memory. So that does a write to memory. Now, forever I thought that this actually happened eagerly in Rails. This happened on boot. I was like, that's why Rails boot is so slow, right? It's got to be this. But it's not. Rails has never ever done this. Now, the downside, I thought that Rails did this eagerly, and it has always done it lazily. And what this process means is that if you're using a threaded web server, your threaded server has to lock. We have to lock every time we go look up a template. Or we may lock when we go look up a template. And the other downside is if you're using a forking server, this wastes memory because it means that all of your child processes are rendering the same template, coming up with the same code and loading it into their memory. So all of your child processes are doing exactly the same thing when it could have been the parent process. So what I want to do is I want to introduce precompiled templates. So what that would mean is that we'd say, okay, I want to get all the templates off your file system, precompile them in the parent process, and then fork all of our children so that the children could share the memory with the parent. If we did that, it means that we'd be able to, if we were precompiling, it means we'd be able to eliminate all of these steps, and in fact, we could actually get rid of the locking process itself because it means these would be read-only. So as the server boots, we compile all the templates and then turn that into a read-only cache, essentially. This means we'd be able to remove locks from threaded servers, and we'd also be able to share memory with parents. So we'd be able to speed up views because we'd no longer have to lock, and we'd be able to drop memory usage on forking processes. So I thought to myself, okay, that's cool. How much memory do we actually save? Like, you know, if we're going to put effort into this process, we should probably figure out like what is our actual savings going to be. So I decided to take a couple templates. These are just, well, I'm showing this to you for fun because this is the joy of programming for me, and I thought this was fun. So what I did is I took ERB templates, and took one of the templates from our machine, or from our website, and I measured the size of it. I don't know if you can read the code, but essentially what we're doing is we say, all right, I'm going to load ERB in, compile it, and then figure out what the size is. And the way we do that is we say, all right, we use object space mem size of all VM instruction sequences there, and what that does, what mem size of all does, is measure the amount of memory that instances of that particular object are consuming inside your process. And these instruction sequence objects are what your Ruby code gets compiled to. So we measure before, compile the template, turn it into a method, and then measure after. And then subtract the two, and we know how much memory that particular template consumes. So if we run this on one of our templates at work, it was about 24K. So that was just one of the templates. Now obviously this is going to change depending on the size of your template. It's going to change depending on what template or what type of templates you do. So the key methods here are object space mem size with all. This measures the size of all of whatever class you pass to it. So you can pass any class to it and it'll tell you. In this case, I'm measuring Ruby VM instruction sequences because that's what I want to know about. We're evaling this code. We're turning these templates into actual Ruby code and evaling it. So the next thing I did is I was like, well, you know, we're going through this thing now where we're converting all of our ERB templates to Haml for some reason. I think that's to prevent me from modifying any of the views, which I'm okay with. Anyway, so I was like, all right, we've actually got one-to-one translations of these ERB templates over to HAML, so I may as well measure them too. So I took that, did exactly the same thing, but with a HAML engine, measured the size of this, did the memory size here, and it's about 25K. So it was slightly larger than the ERB templates, but I just thought that was kind of interesting. So the way to calculate the memory savings for this particular technique is we could say, well, we need to figure out the compiled template size. So figure out how big all the templates are in our system, the compiled template size for all of them, and then divide that by the number of workers that we have, and we should be able to calculate how much memory we save with this particular technique. Now, clearly this is going to depend on your application, because your application may have more views or fewer views than my application does, and your views may be larger or smaller, and we don't know, and I don't know how many workers you're running in production, but I'm pretty sure that this savings will be good for everybody. Everyone will see a savings, I believe. The other weird thing about this is that we were thinking about, well, maybe there's people who have applications with thousands of views, but maybe only one or two of those views are actually used. So we need to take that into consideration. Those particular people are going to see memory bloat because, you know, if they have thousands of views that they've never actually used, we're going to be loading all those into memory. So I think what we're going to be doing is having an option where you can choose to precompile or not. So you can do lazy or not, and check to see which one of those wins for your particular application. The other thing I was thinking is maybe we could have something where you decide which ones are precompiled. So you could say, I know that these particular templates are hot. I want you to precompile those so that we can at least have the memory savings. What's the other issue with that? Too many templates, precompiling. I guess that's it. Anyway, so I think I'm getting close to time here. Rails 4.2, I introduced adequate record. These are speed improvements to active record. I don't want to work on active record anymore for a while. Tired of it. So Rails 5 is going to be adequate view. I suppose it'll also be adequate integration tests. I just want to make it good enough, okay? Just good enough. So, I don't know, I called this talk The Joy of Programming. And for me, the reason programming is fun is because I see it as a puzzle. Like, I love solving all these little weird issues, like looking at things like why, you know, random execution with weak references, or why are these tests so slow, like, and finding these strange bugs, like why is calling trap weird on OS X? I love investigating these super weird issues. But I think most of all is that I love that I can take these things and make slides out of them and show them to people and say, like, this is what I love doing. This is I love solving these weird issues and I love showing them to you. This is the important thing, or the reason I love programming so much is because I can build something and I can actually share it with an audience. So to me, this is the joy of programming, really. So I want to end this off saying thank you very much. I really appreciate you having me here. It's really an honor. So thank you.
No come electro por la vida.